Yes, a 240/120 single-phase 100 amp panel can be fed from two legs of the secondary side of a three-phase 240/120 tap transformer without using the third leg. However, there are important considerations. Firstly, phase balance is critical. When utilizing only two legs of a three-phase transformer, ensuring the load is balanced between these two phases is important. An unbalanced load can lead to current imbalances within the transformer, which can result in overheating and potential component failure. Secondly, consider the maximum current capacity. The maximum current capacity of the single-phase panel is limited by the current capacity of each leg of the transformer. Given a 100 amp panel, a transformer with a secondary current capacity of at least 100 amps per phase is needed. Thirdly, there's neutral bonding. When a three-phase transformer is used to supply a single-phase panel, the neutral must be bonded to the ground. This bonding helps maintain the neutral conductor at the same potential as ground, which helps to prevent electrical hazards. To reiterate the key points, understanding phase balance means that you need to distribute the load as evenly as possible across the two phases you are using. If one phase is significantly more loaded than the other, it can create problems in the transformer and potentially affect other equipment connected to the same electrical system. For the maximum current capacity, it's important not to exceed the rated current of the transformer windings. Even though the panel is rated for 100 amps, the transformer must be capable of supplying that current continuously without overheating. Using a transformer with a higher current rating provides a safety margin and can improve the transformer's lifespan. Neutral bonding is a safety measure that connects the neutral conductor to the grounding system. This connection provides a low impedance path for fault currents to flow back to the source, which helps to trip circuit breakers or fuses quickly in the event of a ground fault. A proper grounding system is essential for electrical safety. Now, considering specific transformer configurations, the most common type of three-phase transformer connection for this application is a delta Y configuration. The delta-connected primary provides a stable voltage source, while the Y-connected secondary provides a neutral point that can be grounded. When connecting the single-phase panel to the three-phase transformer, select any two line conductors from the Y secondary. The voltage between these two lines will be 240 volts. The neutral conductor from the Y secondary is connected to the neutral busbar in the single-phase panel. Also, the ground conductor from the transformer grounding system is connected to the ground busbar in the single-phase panel. Always use appropriately sized conductors for all connections. The conductor size must be sufficient to carry the maximum current that will be drawn by the load connected to the panel. Refer to the National Electrical Code, specifically NEC Table 310.16 for conductor and capacity ratings. Overcurrent protection is another critical aspect. Install appropriately sized circuit breakers or fuses in the single-phase panel to protect the branch circuits in the panel itself from overloads and short circuits. The overcurrent protection devices should be rated to protect the conductors and equipment they are serving. When selecting a transformer, consider its kVA rating. The kVA rating represents the apparent power that the transformer can deliver. To determine the appropriate kVA rating, calculate the total load that will be connected to the single-phase panel. Add up the power requirements of all the individual loads, taking into account any diversity factors or demand factors that may apply. Select a transformer with a kVA rating that is sufficient to supply the total load. Furthermore, harmonics can be an issue in electrical systems, especially when nonlinear loads are present. Nonlinear loads, such as electronic devices and LED lighting, can generate harmonic currents that distort the voltage waveform. These harmonic currents can cause problems in transformers, including overheating and increased losses. To mitigate harmonic problems, consider using harmonic filters or K-rated transformers. K-rated transformers are designed to withstand the effects of harmonic currents. Also, temperature rise is an important consideration for transformer operation. Transformers generate heat as they operate due to losses in the core or in windings. The temperature of the transformer must be kept within acceptable limits to prevent damage to the insulation and other components. Transformers are typically designed to operate at a specific temperature rise above ambient temperature. Make sure that the transformer is installed in a well-ventilated location to allow for adequate cooling. If the transformer is installed in an enclosed space, provide forced air cooling to prevent overheating. Moreover, voltage regulation refers to the ability of a transformer to maintain a constant output voltage under varying load conditions. When the load in the transformer increases, the output voltage may decrease slightly due to internal impedance. Good voltage regulation is important to ensure that equipment connected to the transformer receives a stable voltage supply. Select a transformer with good voltage regulation characteristics to minimize voltage drop under load. Also, efficiency is a measure of how effectively a transformer converts electrical energy from the primary side to the secondary side. Transformers are not perfectly efficient, and some energy is lost in the form of heat. High-efficiency transformers can save energy and reduce operating costs. Select a transformer with high efficiency to minimize energy losses. In addition, impedance is an important parameter that affects the performance of a transformer. The impedance of a transformer limits the amount of current that will flow during a short-circuit condition. A higher impedance transformer will limit the short-circuit current to a greater extent. Select a transformer with an appropriate impedance level to protect the electrical system from damage during short circuits. Also, insulation is a critical component of a transformer. The insulation provides electrical isolation between the windings and the core, and between the windings themselves. The insulation must be able to withstand the voltage stresses that occur during normal operation and during transient events. Select a transformer with high-quality insulation to ensure reliable operation and long life. Regarding transformer taps, some transformers are equipped with taps that allow you to adjust the turns ratio and output voltage. Taps can be used to compensate for voltage variations in the supply voltage or to adjust the output voltage to match the requirements of the load. Make sure that the taps are set to the correct position for the desired output voltage. Furthermore, transformer cooling methods vary depending on the size and design of the transformer. Small transformers may be self-cooled by natural convection. Larger transformers may be cooled by forced air, oil, or water. Select a transformer with an appropriate cooling method to ensure that it operates within its temperature limits. Also, transformer protection devices are essential for protecting the transformer from damage due to overloads, short circuits, and other abnormal conditions. Protection devices include fuses, circuit breakers, and protective relays. Make sure that the transformer is protected by appropriate protection devices. When dealing with transformer installation, install the transformer in accordance with the manufacturer's instructions and all applicable electrical codes. The transformer should be mounted securely and should be protected from physical damage. Provide adequate clearance around the transformer for ventilation and maintenance. Also, grounding is a critical safety requirement for transformers. The transformer must be properly grounded to prevent electrical shock hazards. Ground the transformer enclosure on the neutral conductor of the secondary winding. Use appropriate grounding conductors and grounding techniques. Regarding transformer maintenance, perform regular maintenance on the transformer to ensure that it is operating properly. Inspect the transformer for signs of damage or deterioration. Check the oil level, bushing condition, and connections. Test the insulation resistance and turns ratio. Clean the transformer and remove any debris. Also, transformer testing is an important part of transformer maintenance. Perform regular tests on the transformer to verify its performance and identify any potential problems. Tests include insulation resistance tests, turns ratio tests, and impedance tests. Consult with a qualified electrician or transformer specialist to perform these tests. Consider also transformer noise. Transformers can generate noise due to vibration of the core and windings. The noise level can be reduced by using vibration isolation techniques and by selecting a transformer with a low noise design. In addition, transformer life expectancy is affected by several factors, including operating temperature, load conditions, and maintenance practices. A well-maintained transformer that is operated within its design limits can have a long life expectancy. Proper maintenance and operating practices can extend the life of the transformer. Finally, safety is paramount. Always disconnect power to the transformer before performing any work on it. Use appropriate safety equipment and procedures. Consult with a qualified electrician if you have any questions or concerns. In summary, while it is feasible to power a single-phase panel using two legs of a three-phase transformer, it's critical to address phase balance, current capacity, and neutral bonding, along with other considerations like transformer selection, overcurrent protection, and safety measures. It is also highly recommended to consult with a qualified electrician before undertaking such a project, as they can ensure that the installation is performed safely and in compliance with all applicable electrical codes. Failure to properly consider these factors can lead to electrical hazards, equipment damage, and potential safety risks.